Good morning. Today, I'd like to invite you into a story how SORAMAME was born, what we discovered, and where this idea might take us. My name is Wakiko Takano. I spent about 20 years designing and developing for the webs. About 10 years ago, I started studying physics seriously. 2 years ago I completed my master's degree, and now I continue as a special research fellow. SORAMAME is a smartphone app which can detect charged particles, including cosmic rays. The kanji characters combine sky and bean as a phonetic loanword, representing beans falling from the sky, meaning particles arriving from space. It also works well as a retroactive acronym, scientific observation and research on astroparticles using mobile and accessible methods. While added later, it captures the project's activity perfectly. The first time I heard about projects using smartphone's camera sensor to detect cosmic rays was right after entering graduate school. Out of curiosity, I placed a small radiation source near the camera sensor of my smartphone with the Crayfise app installed and observed what happened. The app reacted clearly. While the radiation source was close, it continuously displayed numerous ripple animations indicating detected signals. It was incredibly fascinating and fun. However, no such app existed for Apple users. That's when I decided to create a simple, easy-to-use app myself. However, when I told my advisor, I want to do the research about cosmic ray observations using smartphones as my master's thesis topic, his reaction was this: "You must be joking." And then the challenge was issued: can you add even a single reliable data point to the cosmic ray spectrum? Since then, my research goal has been to add even a single reliable data point to the cosmic ray spectrum using a CMOS camera sensor. Using a Raspberry Pi and camera sensor with various radiation sources, we were able to observe the tracks of charged particles. Next, we tilted the sensor and measured the tracks. The measured values changed proportionally to the cosine of theta relative to the radiation on the sensor surface, exactly as predicted geometrically. Having confirmed that charged particles could indeed be detected and that changes in particle density could also be observed, we then built and released the first prototype of SORAMAME app. At conferences, people asked the right question: are you sure these are cosmic rays? Isn't this just noise? Seeing charged particles is not the same as proving they are cosmic ray secondaries. Without that proof, it's not a cosmic ray detector. To confirm whether cosmic rays could be detected, we decided to conduct the experiment at higher altitudes. As you know, cosmic ray secondary particles increase with altitude. If the app measured a clear increase during flight, it would be strong evidence that it was capturing genuine cosmic rays. This slide shows the result of a cosmic ray detection test using an iPhone 13 Pro on a flight from Haneda to Bangkok, cruising at around 10,000 meters. The observation was conducted on February 15, 2024, during a commercial flight, with observation time of 4 hours and 40 minutes. In the graph, red lines and bands show the average and standard deviation at ground level, while blue indicates the same during the flight. At high altitude, the detection rate increased from 2.03 to 5.93 signals per 10 minutes. That's nearly 3 times higher than the ground level average. Even with a consumer-grade CMOS sensor, the device showed a clear and stable response to radiation changes at altitude. While we ran the airplane experiment, it wasn't an instant success. At first, we saw almost nothing. After many rounds of algorithm tuning, we finally obtained reliable altitude-dependent measurements. With that in mind, here's a brief technical overview of SORAMAME. At its core is the smartphone CMOS sensor, which records ionization as digital images. When a charged particle passes through, it can leave a small track, a faint line or dot on a dark background, as shown on the left. The app runs in continuous video and analyzes each frame in real time to extract candidate tracks. During setup, the detection threshold auto-adapts to the current noise level. Once a signal exceeds that threshold, the event is logged and uploaded to the cloud. On our website, candidate events appear in real time, and each device has a detection rate graph so users can immediately see activity. On the right is the app interface. Each ring marks the detection location on the sensor. Because sensor pixels map directly to the screen, This view makes it easy to judge whether detections are evenly distributed or dominated by local noise. Each ring shrinks and fades over 12 hours, providing a quick visual history of recent activity. When you use the app, sharing location is optional. If you allow it, your observation point is automatically added to our public map. We blur precise positions to protect personal information. This map is available on the SORAMAME website. After multiple tests at high altitudes, we confirmed the influence of the Earth's magnetic field. Near the equator, the Earth's magnetic field bends incoming cosmic rays, so only higher energy particles can reach the atmosphere. At higher latitudes, the magnetic field is more aligned with the incoming rays, allowing even lower energy particles to enter. Unlike the previous experiment using a smartphone, this time we employed a prototype detector built with a Raspberry Pi and a CMOS sensor. We chose this configuration because consumer devices frequently see new model updates. This allows for a deeper understanding of the long-term potential of CMOS sensors in radiation detection. We compared the increase in cosmic ray observations across 3 flight routes. 1. From Guam near the equator to Japan. 2. From Vancouver to Japan. 3. From Montreal near the pole to Japan. The results confirmed the expected latitude dependence, greater increase near the poles, smaller near the equator. This means the camera sensor could also capture differences in cosmic ray flux caused by the Earth's magnetic field. After presenting those results, the discussion shifted. The question was no longer whether cosmic rays could be detected. Instead, people said, so detection is possible. But cosmic ray air showers with CMOS sensors? Really? Do we need to use camera sensors for this? This doubt became the next driving force. We have now begun experiments using compact CMOS sensors for cosmic ray air shower detection. The challenges are significant, the effective area is small, and the arrival frequency is extremely low. But that is precisely the thrill of the challenge. If we can transform everyday sensors into air shower detectors, it will open new doors for both research and education. Our strategy is to focus on the dense core of showers with the highest particle multiplicity. While running Corsica simulations to predict spatial and temporal patterns, we are deploying a small prototype array using a Raspberry Pi and high-quality camera housed in a waterproof case. Although just beginning, this represents a crucial step toward detecting cosmic ray air showers in real environments using compact consumer hardware. We've looked at how the SORAMAME app was born, how we improved it, and what we're doing now. This slide shows the big picture of the SORAMAME project. Today, there are an estimated 19 billion internet-connected devices worldwide, and many of them contain CMOS cameras. If we use those sensors, we can imagine a planet-scale observation network. This idea also fits naturally with education. In class, students can use the app to compare observations at different altitudes and latitudes, learning about cosmic rays and the Earth's magnetic field and perhaps noticing that Earth is literally receiving particles from the universe. There's also a social dimension. When people everywhere use the same tool to observe the same natural phenomena, it doesn't only advance science, it can also improve equity and quality in education at a global scale. Using the devices we already have, we can invite anyone, anywhere, to observe the cosmic particles that fall equally over the Earth. We believe that simple act carries tremendous potential for discovery, for learning, and for connecting people to the sky. Lastly, a brief introduction to how to use the app. First, please download SORAMAME from the Apple App Store or Google Play. It works on iOS 11 or later and Android 4 or later. When you open it for the first time, the app will ask about location and camera usage. Location is optional, you'll then see the observation screen. Before starting, make sure the rear camera is completely covered so that no light leaks in. Use light blocking tape or place the device in a dark enclosure. If light is detected, the app will show an error. Once it's dark, tap Measure on and Start. For better results, keep the device plugged in, stable, and collect data over a longer period. Please give the app at least the first 3 hours to complete its automatic noise calibration. During this period the detection rate may look unusually high, that's expected. Keep it running. As the threshold adapts, the rate will gradually fall and stabilize at about 1 event every few minutes. That's your cue to begin experiments. Compare different altitudes or latitudes. Please note that sensitivity varies by device. Most models show a clear response to a radiation source, but small altitude differences may not be visible on every phone. In-flight observations is exciting and highly recommended, but network access is often limited on airplanes, and even when available the upload speed may be insufficient. We used a paid network service for our experiment. For the current version, a network connection is required for data to accumulate, so observations cannot proceed offline. An offline save feature is under development. That's the quick guide. With just a few steps, you'll be ready to join global-scale observations with SORAMAME. Today I introduced the SORAMAME project, our smartphone app for observing cosmic rays. I'd be delighted if you download the SORAMAME app and try a few observations yourself. Thank you.